Welcome to Quantum Curious, and in today's lecture, we are going to discuss very basic concepts and applications related to density matrices. So we saw that in previous lecture, what are density matrices and what are their properties, and what are the conditions that are necessary to have a valid density matrices. So today we are going to discuss some extensions of these concepts related to density matrices. And the first concept is the Bloch sphere representation of the density matrix, as we saw that there is a Bloch sphere representation of the single qubits. And then we are going to discuss the tensor product of the density matrices because we sometimes want to know what is the composite system of the subsystem. And then we will see that at last, how can we form the quantum classical state that are the hybrid states of with the help of the density matrices and the concept of the tensor product. So let's start with the concept of the Bloch sphere representation. So we know that we can represent very easily the single qubit state in Bloch sphere, and we could represent it with the help of the Bloch vector. And it is a very good way to visualize the given quantum state and to visualize the operation that we could perform on the quantum state. So generalizing that concept of visualization to the density matrix, we could represent the density matrix with the help of the Pauli matrices and the Bloch vector. So in compact form, we could write it in the form of the dot product of two vectors. So you might be thinking that is it a good or valid way to represent the density matrix? So the answer is that yes, it is a valid way to represent the density matrix because we know that the Pauli matrices X, Y, Z, and the density matrix, the identity matrix form the basis of space of 2 by 2 density matrices, and it could be uh, proof that the tensor product the inner product or the Schmidt product of the any two basis vector should have to be zero. So these all the density matrices or the matrices in the basis set are orthonormal to each other. So this could be proved quite easily by taking the inner product of the corresponding pairs of vectors or matrices from the basis set. So one of the most important fact associated with Bloch sphere representation is the categorization of the pure state and the mixed state. So in the form of the Bloch vector, we could represent or we could identify that which whether the given state is a pure state or a mixed state. So for in order to the given state to be a pure state, their Bloch vector mod square should be equal to 1. And their and if the given state is a mixed state, thus the mod square of the given Bloch vector should be less than 1. So uh, from the visual point of view, we could say that the pure state lies on the surface of the Bloch sphere, and the mixed state lies underneath the surface of the Bloch sphere. So let's move on to the example and how can we explain and with the help of this example, and we will try to understand from that example. So consider we have a general pure state that is a qubit state, and it is a superposition of state 0 and 1. And we could write the given density matrix of that pure state by taking the outer product of the cat and bra. So in order to find the components associated of the Bloch vector of that density matrix, we have to take the trace of that given density matrix with the given Pauli matrix. So in order to find the Vx, that is the X component of the Bloch vector, we have to take the trace of the density matrix with the Pauli X matrix. Similarly, to find Vy, we have to take the trace of density matrix with the Pauli Y. And similarly, to find the the Vz component of the Bloch vector, we have to take the trace of the density matrix and the given Pauli Z matrix. So in that case, we end up with that form of the Bloch vector. And we could see that if we take the mod square, that is the addition of the components, the addition of the squares of these components, we end up with the value of 1. So we could see that our criteria says that the given matrix or density matrix or given quantum state is a pure state. So let's be more specific. So we have a plus state, that is the Hadamard state, and it is an equal superposition of 0 and 1 state. So its density matrix has this form. And if we similarly calculate the given components of Bloch vector as previous, we could find that the Bloch vector has this form. So it is oriented along the x-axis. So we could see that the Bloch vector has mod square is equal to 1, and it uh, it says that the given state is a pure state. So let's take the example of mixed state, that is the maximally mixed state, and it has the density matrix form as this. And if we similarly calculate the Bloch vector of that density matrix, we end up with that a Bloch vector. So it we could clearly see that the given mixed state is categorized as our criterion as the mixed state, that is the maximally mixed state. So that's how we could categorize the density matrices on the basis of Bloch vector, and we could visualize them in the Bloch sphere. So now move on to the concept of the tensor product. So we saw that how can we form the composite states from the individual states in the form of the single qubits, or in the case of the single qubits. So we could generalize that concept for the density matrices. So we have individual subsystems, and they are represented by row A and row B. So we want to know that what is the form of the composite system. So we could get the composite system state, that is the density matrix state, from the tensor product of the its density matrices of the individual subsystems. So in that case, we have row A that has elements M11, M12, M21, M22, and similarly we have row B that is represented as a density as a matrix having elements N11, N12, N21, and N22. So in order to perform the tensor product of the given matrices, we have to move one matrix into the other. So we move the density matrix associated with the system B into the matrix of row A. So similarly, we are end up with the scalar product of the uh, scalar product of the given matrix. So that could be performed very easily, and we end up with a large matrix, and it has the dimension of 4 by 4. So we started with the 2 by 2 matrices, that is the individual matrices, and the composite system has the double amount of the dimension that was previous that as compared to the previous or the original density matrices. So the it is a rule, or you could say that it is a very helpful trick that to find the dimension of the composite system. So if we start with the k by k matrices, we will end up with the 2k by 2k matrix. So that is the case for density matrices or their composite systems. So as we know that the matrix multiplication is non-commutative. So similarly, the tensor product of two density matrices or multiple density matrices is non-commutative. So if we change the order of the tensor product of the given two matrices, we will end up with a different result. So we have to take care of that fact in our calculations. So the last concept is the classical quantum states, and these are usually called the hybrid states because they have some classical part and some quantum part. And these classical states are very important in quantum cryptography because in security analysis we usually have some classical states formed by Alice, and Eve might have some side information associated with that classical state. So how could we represent that given state in form of the density matrix? So let's start with the representation of the classical state. So we have some classical variables that are represented by set X, and they have D minus one values. And each value has some probability distribution associated with it. So we could represent these values in the form of the cat. So we have a set that has some values and they are represented by standard basis. And we could represent the given set having some probability distribution associated with each element of the set with the help of that density of the density matrix. So density matrix, we could see that the density matrix is showing that the probability associated with each element has position diagonal along the diagonal of the given matrix. So if we perform some measurement associated with the standard basis, we will end up with that probability distribution of the given outcome. So that's how we could represent the given classical states with the help of density matrix. So consider we have some X state in standard basis and they have some probability distribution Px associated with them and the associated quantum state associated the side information that is the quantum state associated with that classical states have the form PQX. So to represent the whole state, we could use the concept of the density matrices and the tensor product. So we are just taking the tensor product of the classical states and the given quantum state. So consider we have a process that is forming zero state and side information with quantum information of maximally mixed state, and it is also preparing some kind of classical state that is the one state and having side information plus state. And the process is quite random because the probability distribution of both states the is half. So how could we write the given state in with the help of the density matrix concept? So this is how we could done that, and this is the Hall process, the density matrix given by the Hall process. So that is the uh, main, we could say, the concept of the given classical quantum states. And this is how we could write the classical quantum state given by any process or any mechanism. So in today's lecture, we saw that how could we represent the density matrices in the Bloch sphere, and we saw that the criterion that categorize the mixed states and the pure states. And then we saw that how could we represent the composite states with the help of the tensor product. And at last, we saw that how we could write the given hybrid states that are the classical quantum states with the help of the density matrix concept and the tensor product. So that is for today's. Don't forget to like, share, and subscribe to Quantum Theories.